Lesson: Theoretical Models of AI in Network Security. The application of theoretical models of artificial intelligence in network security is a crucial development in modern cybersecurity. These models provide advanced methodologies to predict, detect, and respond to an array of cyber threats. Traditional network security measures often fail to keep up with the sophistication of contemporary cyber attacks. AI models, through their ability to learn and adapt, offer a more dynamic and robust defense mechanism. Machine learning, a subset of AI, plays a pivotal role in these theoretical models. By analyzing vast datasets, ML algorithms can identify patterns and anomalies that might indicate a security threat. For instance, supervised learning models can be trained on historical data of network traffic to detect known types of intrusions. Once trained, these models can identify similar patterns in real-time network traffic, flagging potential threats for further investigation. This approach is particularly effective against known threats but may struggle with novel or zero-day attacks, which are not part of the training data. Unsupervised learning models offer a solution to this limitation by identifying anomalies without prior labeling. These models can detect deviations from the established norm, which may indicate new or previously unseen threats. For instance, clustering algorithms can group network activities into clusters of normal behavior. Any deviation from these clusters could suggest an anomaly, prompting further security checks. This method enhances the ability to detect novel threats but may also produce more false positives, requiring fine-tuning to balance sensitivity and specificity. Deep learning, another advanced AI technique, leverages neural networks with multiple layers to enhance network security. These models can automatically learn representations from raw data, making them highly effective for tasks such as malware detection and network traffic analysis. Convolutional neural networks, for example, have been used to detect malicious software by analyzing binary files as if they were images, identifying features that distinguish malware from benign software. Similarly, recurrent neural networks, particularly long short-term memory networks, are adept at analyzing sequences of data, making them suitable for detecting patterns in network traffic over time. Incorporating AI into network security also involves reinforcement learning, where systems learn optimal strategies through trial and error. RL models can adapt to changing network environments and threat landscapes by continuously learning from interactions with the network. For example, an RL-based intrusion detection system can dynamically adjust its detection policies based on feedback from its performance, improving its accuracy over time. This adaptability makes RL particularly valuable in combating evolving threats. The integration of AI in network security is not without challenges. One significant issue is the quality and quantity of data required to train these models effectively. High-quality, labeled datasets are essential for supervised learning, while large volumes of data are necessary for deep learning models to generalize well. However, obtaining such data can be difficult due to privacy concerns and the proprietary nature of network traffic data. Furthermore, the computational resources required for training deep learning models can be substantial, posing a barrier for organizations with limited resources. Another challenge is the interpretability of AI models, particularly deep learning models, which are often considered black boxes. Understanding how these models make decisions is crucial for gaining trust and ensuring compliance with regulations. Techniques such as SHAP and LIME have been developed to interpret model predictions, providing insights into the features that influence decisions. These methods help enhance the transparency of AI models, making them more acceptable for deployment in network security. Despite these challenges, the benefits of AI in network security are undeniable. AI models can process and analyze data at a scale and speed unattainable by human analysts, providing real-time threat detection and response. For example, a study by IBM found that organizations using AI and automation in their cybersecurity efforts reduced the average time to identify and contain a data breach by 27% compared to those that did not use these technologies. This reduction in response time is critical in minimizing the damage caused by cyber attacks. Moreover, AI can enhance the efficiency of security operations by automating routine tasks, allowing human analysts to focus on more complex issues. For instance, AI-powered systems can automatically filter out false positives, reducing the workload on security teams and enabling them to concentrate on genuine threats. This automation also helps address the shortage of skilled cybersecurity professionals, a significant challenge for many organizations. AI models can also facilitate proactive threat hunting, where security teams actively search for potential threats rather than waiting for alerts. By analyzing network traffic and system logs, AI models can identify indicators of compromise that may suggest an ongoing or imminent attack. This proactive approach helps organizations stay ahead of cyber adversaries, reducing the likelihood of successful attacks. The future of AI in network security looks promising, with ongoing research and development aimed at addressing current limitations and enhancing capabilities. For instance, federated learning, a technique that enables AI models to learn from decentralized data sources without sharing raw data, offers a potential solution to data privacy concerns. By training models on data from multiple organizations while keeping the data local, federated learning can improve the robustness of AI models without compromising privacy. Another emerging area is the use of adversarial machine learning to improve the resilience of AI models against attacks designed to deceive them. By simulating adversarial attacks during the training process, AI models can learn to recognize and resist such attempts, enhancing their robustness. This approach is crucial in ensuring that AI models remain effective even when targeted by sophisticated cyber adversaries. In conclusion, theoretical models of AI offer significant advancements in network security, providing dynamic and adaptive defense mechanisms against evolving cyber threats. Machine learning, deep learning, and reinforcement learning models each contribute unique strengths, from detecting known intrusions to identifying novel threats and adapting to changing environments. Despite challenges related to data quality, computational resources, and model interpretability, the benefits of AI in network security, including enhanced detection capabilities, reduced response times, and increased operational efficiency, underscore its critical role in modern cybersecurity. Ongoing research and development promise to further enhance these capabilities, paving the way for more robust and resilient network security solutions.